Hello everyone, this is Dr. Abdul Pasha. So coming to our course name is Power System Operation and Control. So we are in the module 2 case, started with the speed governing mechanism. We already discussed some points regarding the configuration of speed governing mechanism, what are the main features of speed governing mechanism and what are the parameters we considered. Those are the things we discussed. So here today's class I am going to discuss about derivation for small signal transfer function. So the derivation for small signal transfer function is relevant to the speed governing mechanism case. We derived some considerations in a small signal transfer function and the extended analysis is carried here, and this may be the replica of a concept of the speed governing mechanism. So once again, coming to this topic, small signal transfer function derivation, here we are going to discuss some key points regarding speed governing mechanism. That is, the first one is governor. So we already discussed this governor mechanism. So power system is basically depend upon the synchronous generator. Here synchronous generator means our alternator which produces the power, and it is satisfactorily performed. That means based on the satisfactory operation of the alternator or generator, the developed power will depends. So when it is good 100% means then the produced power is to be enough more to meet the load requirement. So here the important control loops in the system are basically, one is a frequency control, another one is automatic voltage. So these are the two loops which maintains the control, that is frequency control, and second one is automatic voltage control. So coming to the first parameter, that is called frequency control. What happened here means, this is achieved through the generator control mechanism. That means governing systems for thermal and hydel generating plants are different in nature, since the inertia of water that flows into the turbine presents additional constraints. So these are not present with the steam flow in a thermal power plant, but however the basic principle is still will be same. That is, speed of the shaft is sensed and compared with the reference, and feedback signal is utilized to increase or decrease the power generated by controlling the inlet valve to turbine of steam or water. So likewise frequency control is achieved. Next case is speed governing mechanism. So in this speed governing mechanism, it includes some following elements or parts. That is a speed governor. So it is an error sensing device in load frequency control. So it is going to include all the elements so that are directly responsive to speed and influence other elements of the system to initiate the action. So here one more block is governor controlled valves. So what are governor controlled valves means? They control the input to the turbine and are actuated by the speed control mechanism. So governor controlled valves are ready to make the control over the input to the turbine, and they will be actuated by the speed control mechanism. So coming to speed control mechanism, it includes all the equipments like levers, linkages, servo motors, amplifying devices and relays. So they are placed between the speed governor and governor controlled valves. So what happened with this means, one of the speed changer is taken place, that is it is going to ready to enable the speed governor system to adjust the speed of the generator unit while it is in operation case. So this is the block diagram showing how speed governing mechanism is existing. So this block contains the speed changer. This is the speed changer block. Here we will apply the lower or raising the flow rate to the speed changer. There are some existing blocks in this, that is XA, XB, this is XA, this is XB, and this will be XC, and this will be XD, and we have XE. So these are the blocks where your flow may be controlled here in this case. That means the speed changer is provided at respective blocks. There may be expectation of every case change in XA, change in XB, change in XC, change in XD, change in XC. Like that every case is expecting here. So with these blocks we are going to make the change of the flow over. And the respective blocks with the currents I1, I2, I3, I4 are provided, and the steam flow is going to be controlled here by the piston valve. The main piston will ready to make the control over this operation. That means the pilot valve is connected at the point of XD. So here high pressure oil is supposed to be taken place at this block. So likewise the pilot valve and higher pressure coils are connected. So when speed or frequency are going to be increases, here the main objective is to reduce the steam primarily. That means primary control over is going to be takes place. That is with fly ball goes up and point B also goes up, point C goes down, and point D comes down. Pilot valve will going to be down, and oil through the lower chamber is going to be maintained, and the main piston is going to take place its action up and down, and valves are going to be closed and open. Then steam actions are going to be decreases and increases. So based upon these consideration of parameters, the speed governing mechanism is going to be operated. So when speed or frequency increases, then according to that we are going to adjust the knob of the system, and we need to reduce the steam, means control over the steam case. There will be control over the steam case primarily, and when it goes increase in order, that means fly ball goes up. When it is goes decremental order, then fly ball goes down. So here point goes up and point C goes down, and point D comes down, means according to that the piston movement, the force of action will be going to take place. Then oil through the power chamber is lower, that is happening in the main piston up and down. So here it enables that speed governor system to adjust the speed of the generator unit while it is in operation. That means pilot valve is going to operate. That means pilot valve is denoted with V. It is going to operate to increase or decrease the opening of the steam. That will be taken place with the inlet valve V. So let here XB and XCR be the changes in the piston. Then we are going to change its position of the pilot valve as a V, and the control valve V responding to the changes in the governor positions. So here XA is due to the load impact when the pilot valve is closed, and XB is 0 and XC is double equals to 0, means the control valve is not completely closed. That means as the unit has to supply its no load losses, then we need to assume that let the no load angular speed of the turbine is considered. So based on these constraints, we are going to operate the speed governing mechanism. Speed governing mechanism. So these are the constraints we are going to be considered to well operate of the speed governor mechanism. So here as the load applied is considered, then speed falls, and through the linkages the governor is ready to operate to move the piston P downwards along with the points A and B. So pilot valve V admits soil under N and lifts it up so that input is increased and speed is going to be rises. So if the link B is removed, then the pilot valve comes to the rest. Then what happens means only when the speed returns to its original value, an isochronous characteristic will be obtained. So with that certain conditions of the arrangements, speed is going to be restored to its preloaded condition. So with this link of the consideration B, steady state is reached at a speed slightly lower than the no load speed and giving to the drooping characteristics for the governor system. So a finite value of the steady state speed regulation is achieved with this arrangement. So for a given speed change or position, the per unit steady state speed regulation is also defined here. That is steady state speed regulation equals to N0 minus Nr by N, where N0 is the speed at no load, Nr is the rated speed, N is the speed at the rated load. So here one of the parameter achieved suitably is that is load frequency control. So what happens with this load control means load frequency control. The following requirements are to be fulfilled for successful operation of the system. The first one is generation must be adequate to meet all the load demand, and system frequency must be maintained with narrow and rigid limits. System voltage profile must be maintained with reasonable limits and in case of interconnected operation. So tie line power flows must be maintained at the specified values. So when real power balance is taken place in between generation and demand, it is achieved the frequency specification. So which is happened automatically with the satisfied values. Similarly, with a balance between reactive power generation and demand, voltage profile is also maintained with the prescribed limits. So that means under steady state conditions, total real power generation in the system is going to be equal to the total megawatt demand. That means it will be added to the real power losses. Any difference is immediately indicated by a change in speed or frequency. So generators are fitted with the speed governors which will have varying characteristics. That means different sensitivities, deadbands, responses, times and drooping characteristics are obtained. So here they will adjust the input to match the demand with their limits. So any changes in local demand with the permissible limits, they are absorbed by the generators in the system in a random manner. That means an independent aim of the automatic generation control is to be rescheduled to the generation changes that should be pre-selected machines in the system after the governors have accommodated to the load changes in a random manner. So thus here additional or supplementary regulatory devices are required along with the governors. So they will be ready to suitable for proper regulation of the system. So here the control of the generation is in this manner, it is termed as load frequency control. So here for interconnected operation, what is happened means the last of the four requirements, whatever we mentioned here. So these requirements are earlier is fulfilled by deriving an error signal from the deviations in the specified tie line power. That should be flows to the neighboring utilities and adding this signal to the control signal of the load frequency control system. So they should meet the generation which should not be adequate to balance the load demand. So it is imperative to that one of the following alternatives they will be considered for keeping the system in operating condition. So here the first parameter that should be meeting the criteria is starting the fast peaking units. That means maximum limits will be applied here. So second consideration is load shedding for unimportant loads, and generation is going to be rescheduled. So these are the parameters we must consider for a suitable operation of the load frequency of the control system. So here for deriving the small signal transfer function of the speed governor mechanism, so it is apparent from the parameters that voltage specifications are not stringent, which should not be considered easily. So load frequency control is achieved by far of the most important in power system control. That means this is the actual output, this is the control over, this is the turbo generator. So here the sensor is connected to through the actual output to the given control action. And similarly here one more control action provided to the second generator, that is turbo generator 2. So this actual sensor is connected to the actual output. And one more system is connected as a turbo generator N. This is also provided by one of the control parameter, which is connected to the actual output also, and it is given with the sensor device. Here PG1 is one of the turbo generator 1 parameter, and PG2 is generator 2 parameter, and for n number of generators the PGN will be existing. That means all these turbo generator 1, turbo generator 2, turbo generator N, all these will be summed together here as PG1 plus PG2 plus so on up to PG. So this will be as the summing point, sigma PGN. This can going to be divided as to the tie line powers. That means this will be indicated with 2. So likewise, for every turbo generator, the actual output is again coincide to the given input reference parameter. It may be for generator 1, it may be for generator 2, it may be for generator N. So like that, for every case, the actual output will be represented here, and it will be connected to various tie lines. So after the speed or frequency fall, due to reduction in stored energy in the rotors, they has taken place. The drop is sensed by the governors, and they divide the load increment between the machines. They are determined by the groups. So which will be into the respective governor characteristics. So there will be subsequently secondary controls. They will restore the system frequency to its normal value by readjusting the governor mechanism characteristics. So here we are going to discuss with one more parameter with automatic load frequency control. Earlier we discussed the load frequency control mechanism. This is going to be automatic load frequency control, that is ALFC. So here ALFC is to be the control over the frequency deviations by maintaining the real power balance in the system. So here the main function of the ALFCs are, first one is to maintain the steady state frequency, and second one is to control the tie line flows. Third one is to distribute the load among the participating generating units. So the control signals are the tie line deviations. That means delta P tie line, that is considered as measured from the tie line inflows. So and the frequency deviations are obtained with the delta F, that is obtained by measuring the angle deviation delta delta. So this is called angle deviation delta delta. Coming to here, error signals like delta F and tie line delta are amplified, mixed and transformed to the real power signal. So which then controls the valve position, and depending upon the valve position, the turbine changes its output power to establish the real power balance. So the complete control over the blocks are represented here. From here, this section steam waste is going to be given. So here valve gates are going to be controlled, which is going to be connected to the turbine mechanism, and this setup is connected to the generator G, and this is going to be tie line to the power network case. So this entire process is connected to the valve gate and the governor mechanism. So these are going to be connected. So this is the basic schematic representation of automatic load frequency control system. So here in this block, based on the given input steam or water levels, the automatic load frequency control valves are going to be operated, and based on that the turbine action is going to be taken place. So for the analysis of the models for each blocks, whatever we represented here, they are going to be required to modify. That means the generator and the electrical load constitutes the power system, and the valve and the hydraulic amplifiers are going to represent the speed governing mechanism. So by considering the swing equation from power system network analysis, so generator can be using the swing equation. With that swing equation, generator can be remodeled by one of the parameter delta delta pm minus delta p. So here delta pm minus delta p is one of the swing equation parameter, which is going to be derived here for consideration of the system. So here delta pm of s is connected to the reference signal, and this reference signal is connected here, which is provided with the input action delta p of s. So which is going to be connected to 1 by 2 hs, which is about delta w of s. So here it will represent the block diagram of the generator. So here load on the system is completely composite, and it contains a frequency independent component, and a frequency dependent component also going to be connected here. The load can be written as P equals to P naught plus Pm. That means delta PDF of S connected and delta PM of S connected to the reference signal, and which is going to be tie line to the 1 by 2 Hs. And this action is going to be feedback to the delta W of S to the D section, and this D section is reverse back. This all components are connected to delta PM of S. This is control over to this block, and this is called delta P naught of S. This block is going to be connected to 1 by 2 Hs plus D block. So this will represent the output section. So here generator and load sections are going to be tie-lined with various block parameters. It may be due to delta PDF of S, PM of S, W of S, PG of S. Like that, various parameters are going to be considered here. So here the variables representing are P is the changes in the load case, P naught is the frequency independent load component, PF is the frequency dependent load component. PF is here equals to D, where D is called the frequency characteristics of the load, and it is also known as damping constant. This is also known as damping constant, and it is expressed in percentage change in load for 1% change in the frequency case. So here, if D value is maintained 1.5%, then a 1% change in frequency is going to be causes. That means 1.5% of change in load is going to be expected. So the combined generator and the load that may be constituting the power system can then be represented like this. That means delta PV of S will be considered as one of the variable, and the delta PM of S another variable. All these two will be tie-lined to KT by 1 plus STT. So this is one of the turbine model, and this is represented with G of S into delta PM by delta PV of S, which is K by 1 plus STT. So this is KT, and this is delta PM of S. This is delta PV of S. These are the variables we are going to represent here, and this will represent the basic turbine model. So based on the basic turbine model representing variables, the turbine will going to operate. So here GT of S is the transfer function of the turbine, and delta PV of S is the change in valve output. This is due to the action that PM of S is the changes in the turbine output. So then the governor can easily be modified and modeled according to the given diagram. So output of the governor is going to be represented with the reference point, where delta P reference is the reference set of power, and delta W by R is the power given by the governor speed characteristic. So hydraulic amplifier transforms the signal PG into valve or gate position that is corresponding to the power PV. So likewise, we can manipulate these conditions with this power PV of S equals to kg by 1 plus STG underscore of PG of S. That means this is representing one of the transfer function of the generator case. So delta PG of S is connected to Ks by 1 plus STG with the delta PV of S, where delta P reference of S is connected to the one of the summing point, and this will make the control over. So delta Pg of S is connected to Kg by 1 plus St. So this means this will be representing delta PV of S. So this block is going to connect it to 1 by R condition with the delta W of S by delta F of S. So these variables representing the conditions of the power system network under suitable conditions. So whatever the constraints we consider as equality and inequality conditions, then they are ready to make the system under stable operating conditions. So based on that conditions, the transfer function parameters are going to be considered a constant. So with these parameters of delta Pg and delta Pv, the response of the system will depend. So it may be manually increase in order or decrease in order, that will be suitably controlled by the various control blocks. So we may use various control here, and that is going to operate the transfer function of the system. So these are some of the references that I have selected here, and with these conditions we can make the governor mechanism to the suitable conditions to start over the power system network operation. And the parameters whichever we represented here as in the manner of turbine model means they are suitable to the extent case only. But large turbo generators, when they are operating with more frequency, means the control over action is going to be simulated here under various constraints. So those constraints are within the permissible limits, and the limits may be extended according to the PE, P0, PF. And also frequency characteristics of the load may going to be changed, which will be under damping range, or which may also express it in percentage change. So there may be the expectancy of 1% change in frequency. So that also we need to consider. If not, there will not be 1% change in frequency, then the system may going to collapse. So that's why we need to expect some sort of change. Based on the frequency change are only your variables PE, P0, PF and D are going to be suitably operated. So when their sum is made means that blocks are going to be created separately. So based on that swing equation parameter, we are going to consider the suitable response of the system. So this will give the stability conditions of the system. So based on that, the levels of the modules are going to be set to the set points. So these set points are ready to operate, and they will reflect it to the variables whatever we assumed here. So with these parameters, we can make the small changes in the signal transfer function model, which will reflect the changes in parameters of the turbine model system. So with this, we will conclude for this session, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.